Yesterday we were having a look at what vibration is all about. Basically, we see that vibration is something where things go in a repeated fashion. And although, we cannot say it's repeated, typically it's a process where things are not steady or at rest. There's a change. The change happens with time. It means that what is there, for example, this mouse, if I leave it like this undisturbed, it is going to be the same in terms of position, in terms of whatever, till something changes its position. So it means that it's what we call as being at rest. It's what is called at being at rest. Okay. So then we saw that vibration can be a free vibration or it can be a forced vibration. There are two kinds of vibrations which we mentioned. Okay. Now, if you look at this was the free vibration. The vibration continues indefinitely. The vibration continues indefinitely. And then we had the underdamped vibration, okay, where we had basically the vibration dying out. It started to reduce its amplitude till it came to rest. Okay. And then we saw the critically damped system where the particle comes to rest without oscillation. There is a change. The change was in a manner that it didn't cause an oscillation. And what we see is if a material is damped, vibration ceases. So if you are damping it, when you are under damping it, it damps over a period of time, much like a bell. When you strike the bell, the sound keeps on reducing till you can't hear it. And if you look at a damped system, a very nicely damped system, it's going to die immediately. Just have a look, if you see people beating the drum and playing on the drum, they strike it and then they keep their hand on it sometimes if they want the sound to stop quickly. Okay, so that means they are damping the energy. In other words, when they keep their hand on that vibrating membrane, the energy is brought to zero, or the energy that causes vibration is brought to zero very, very quickly. So this is an example of damping. So when you are having a critically damped system, the damping is such that it will not allow oscillation and the body comes to rest very quickly. And the over damped system also doesn't exhibit oscillation. It doesn't exhibit oscillation. But what actually happens is the member comes to rest much more faster than otherwise. Okay, it comes to rest much more faster than otherwise. What do I mean by otherwise? When I say otherwise, I mean that there's no nothing to stop the object from oscillating. Okay. Sorry. Okay. See, suppose you are going.
That is zero.
I'm sorry.
That will stop in quicker manner.
It will be the shortest time possible in which it can stop vibrating. That is the critically damped system. Over damped systems also don't exhibit vibration, but then they come to rest taking a little more time than when it is critically damped. Okay, so that is the that is the difference between the two. I hope you're clear now. Okay, so so this is the difference between the critically damped systems and the systems which are not so, which are under damped. I'm sorry, which are over damped. Okay, under damped system will exhibit vibration. Okay, under damped systems will exhibit vibration. So that is probably the difference between the under damped systems and the critically damped systems. Okay, any questions, any other question you have? Right. Okay, so everywhere we were also seeing that vibration is not particularly a bad thing. Vibration is not particularly a bad thing, but in many cases, they are undesirable. Okay, why are they undesirable? Because they can cause unnecessary damage, okay, damage which you don't expect it to happen. Okay, so that's why we kind of call it as unnecessary vibration, right? Okay.
Any examples?
See, for example, if suppose there, I think we were talking about the case where we were having the uh, washing machine. So when the washing machine is vibrating, is it desirable or undesirable? The AC unit was another example which we saw. Whenever there is a noise, definitely there is a vibration which is annoying to the human ear. Again, you can also see that the precision motors and other things are not, they are getting out of alignment, and they are not going to perform well through the service. And if you look at another thing where vibration is undesirable is, I don't know, if you raise your car or motorcycle, especially the older vehicles, in bus and all, you'll see the mirror starts to shake, and you think you can see anything which is coming in the back very clearly. Okay, that is another case where vibration is not desirable. Again, vibration is not desirable on a floor. If you walk on some floors, you will find that the entire floor is starting to oscillate. Why is it undesirable? People start to feel the building is unsafe. Although it is perfectly safe, it becomes unsafe. So we can keep on talking about a lot of examples where vibrations are not desirable, and where vibrations are desirable, we told that when the soil is being compacted by vibro compactor, the entire process is desirable. Okay. Now this is a very good time for you to make probably a few notes, because these are examples which are probably very good for you to understand, but it's very easy to forget also. So, yep, just get some water. So we see that there can be good vibrations, there can be bad vibrations. We also saw that massages is a kind of good vibration. Your heart beating itself is a good vibration, right? One of the other things we saw was the swing. The swing is an example of probably what we can call as a good vibration, because children love what is happening on the swing. We are talking that the swing has what is known as a time period. That means the rate at which the swing oscillates. Okay. So now let's just have a short video to understand or try to understand this.
Are those adults?
No. I don't see any kids. I
You don't see any adults? This is priceless. I'm going to post
What are you
this.
seeing here?
Oh, man.
Yeah. How many people are swinging? How many people are swinging? 3 people are swinging. Okay. Now, when you
Whoa.
are getting a chance to review this video, just
Don't
see
fall out of
the
there.
top bar over here. Okay. The top bar,
Cam's
I'll just take the
going to go
pointer.
all the way around.
Yeah, it bends, but you see in certain positions when all the 3 are almost going the same direction, that time it's appearing to bend more, as in this time, but otherwise the amount or rate at which it's bending is not actually visible, literally speaking. Another thing, you can see there are 3 people. Okay, I will let you judge who's the heavier of the 3. And the length of the swing is the same, but the time period or the rate at which it's oscillating is not the same. Okay. Now there is a small thing which I must add. If you see, the people are also swinging their feet, right? When they swing their feet differently, you will find that when they're going forward, they are swinging their legs out, and then when they're going
Are
back,
those
they push their
adults?
legs backward. Now what happens here, the length, okay, the length
You don't
from
see any
this point
adults.
till the tip of the toe changes.
This is priceless. I'm
Now
going
you
to
would have
post
found
this.
that moment of inertia is higher whenever the mass
Oh,
is
man.
distributed away from the body, right? So this kind of comes into the picture here, right? This is indirectly like your
Whoa.
rotational, what do you call it? The
Don't fall out of
component which
there.
helps you get better rotation. I can kind
Cam's
of
going to go all the
relate
way
it to
around.
the vibrating length also, length of the element. Okay. Now the other thing is the mass is constant. Okay, and if suppose this swing was to come to rest, the hinges which are here or the pins about which this swing is held in position is going to play a very critical role in the sense that if it is rusted, if it's going to be, it's going to prevent the motion from being very easy. It's going to prevent the motion from being very easy, right? And yesterday I wanted to show you this. I wanted to show you this video, and this is that speaker going at 20 hertz. And when we are what is happening here is the velocity of the material is keeping on changing, okay, and this is a non-Newtonian fluid. The Newtonian fluid viscosity, like you relate it to the velocity. Okay, here again there's a velocity, but see what happens, the viscosity is increasing in this case. Okay, so it seems to be a very nice example to have a look at, okay, because it's forming amazing shapes. Okay, so you will be coming to this part a little later. Okay, so vibration, one of the things which vibration can do is seen here. This is that cornstarch fluid which we had. Okay, in the previous case, remember mass changed and so the time period changed. Okay, now I am going to come to some other terms which we are going to be using later, but I think it's instructive to understand them before you go there. Now have a look at this setup. Here there is a system which is exciting this shake table, right? This rod is moving forward and backward, and we are having the table move. Okay, now in this case they are going to gradually increase the rate at which the table moves. Okay, and you please see what happens. At the same rate of motion, the rate of motion is the same, but if you see, one of the system is showing more response, or it responds to the oscillation more. Okay, at low frequency, if you see, for the given mass, okay, and the vibrating length, okay, the response is different. It's not the same. One is having marked change, and because both of them are almost vibrating at the same, this is the natural frequency of the first system, so it is, the excitation is showing a very huge response. The excitation is showing a very huge response. Now this keeps on increasing, the frequency is keeping on increasing, and as the frequency increases, the response of the first element is reducing, but the second element starts to increase. The second element starts to increase, and then this keeps on going. The vibration, the intensity of vibration is the same. This is that the amplitude is the same. However, the base excitation amplitude is the same, but the element, see, at 6.35 hertz, the entire system is also participating in the is participating more in the response to the base excitation. Okay, or in other words, the forcing frequency. Then the forcing frequency is kept on increasing. Amplitude is the same for all the three systems. Okay, so now if you see, the first mass is almost oscillating with the same frequency as the base. Slowly the second system is also coming to rest, whereas the third system is starting to increase. Okay. So there are three elements, the addition, when they are giving some additional force, they are giving some additional force, they are able to swing with greater amplitude. Okay. The time period is remaining the same or approximately the same, but then their amplitude keeps on increasing. In fact, if you just keep pumping your leg properly, you without anybody from the outside moving, you still can achieve the motion. Okay. One of the things people do on the swing also is when they are at the highest point, they go up a little, like maybe move their neck up a little and then come down. Now this makes a slight increase in the potential energy. So whatever is the energy that you might have lost through friction, through air resistance, you are making it up from maybe some of your slight motions. So that is a different concept. The swing shows or demonstrates to us that irrespective of the many other parameters, the time period is more or less going to be the same. Okay, that's what I told. Like you can weigh yourself, sit on the swing, the vibrating length, try to see the frequency. The frequency is going to be the same, but your amplitude need not be the same. Okay, and again, when both the swings are in phase, that means the force which the system experiences is going to be more. Maybe there you can have some resonance. Okay, any doubts in what we are seeing now? Right. So please go through this. Okay, this is a very nice video which I happen to find. Now I have found a couple of other videos also which I feel is instructive. Now we are going to see what are known as Chaladni's patterns, which are getting created when this beam is getting excited. Now please have a look at it, because we are going to see a very important concept called mode shape based on this. Okay. Now what is mode shape? Mode shape is for a particular frequency, a system will take a specific shape when it vibrates. This is known as a mode shape. Okay. So now this experiment shows us the mode shapes, and let me just remove my laser pointer, then only I can start the video. Here it is. So we can have many modes. So this mode particularly is the bending mode. Look, it's a system to excite the beam. Okay, and the beam is going to show bending mode. Okay, so bending mode, if you see, when you saw it, they showed 2 points. Now look, this is the second bending mode. We got 1, 2, 3 nodes. Okay, and that is what is, and the ends are free basically. Okay, so now let's see what happens. Can you see the sand is getting pushed away from the most of the vibrating element. It's only coming to the places where it is at rest. In fact, you can see it in the fan also. The dust collects at the place where the velocity is the least. So here, look at this. The pin is almost getting thrown out. When he's keeping the pin on that scale, it's getting thrown out. But when he's coming closer to this point, see, it's at rest. It's not vibrating. Okay. So this means the shape which you saw is happening. Now you can see the middle, it's not able to even be kept. Right. So here you just study the other patterns which are also being demonstrated here. This is a very interesting video for understanding. Perfect, right? This is the third bending mode. So again, you can, with your past experience, now you say that there are 4 modes. Okay. So here we go. So they are increasing the frequency. So when the third mode, whatever was at rest, now you see the sand is starting to move towards the place where there is not much vibration. So he's just having to add more sand, and now you are going to see the 4 modes of this one, vibration. So again, now there is going to be 5. Please keep it in mind. that nodes and antinodes are being formed, and you can find that you have studied already this in your physics in open pipe or closed pipe, both of them. Remember, node is formed at the closed end, antinode is formed at the open end. Now we are going to other things. Initially we saw the bending modes. Now see, this is a torsion mode or a twisting mode. So these are the places where we are going to have least vibrations. Okay. So now I will look at this. This is a torsional mode. Wow, resulted nothing's happened. Right? Initially, if you see perpendicular to this only, the sand was getting at rest, being at rest. Now see, you can see how what's happening there. It's still in motion. If it's going a little away from the center, the sand is getting pushed back, but it doesn't like to go because this is the place where it is at least motion. No? Very nice. Okay, one of the things I want you to look at is when were more number of nodes getting formed? When the frequency was low or when the frequency was higher? So what is low frequency? That's higher frequency. Okay, so which of these two caused more number of nodes? I guess you should go back. Once this video is put up, I want you to study this part. See when the nodes were more. This is a very important thing. And I'm going to now probably go ahead and show you one more very interesting video. This video will also help you understand this concept of mode shapes a lot. Okay.
Hello and welcome to this week's edition of Chalk Talk. Our subject this week is the subject of resonance. Resonance is a pretty common problem in industry today. Some people estimate about a third of your machines have vibration on them that is being magnified by resonance or natural frequencies. One of the ways we have of identifying a resonance problem is to plot out a resonance mode shape. When structures vibrate due to resonance, they tend to vibrate with a resonant mode shape. There are various resonant mode shapes. For example, if the structure was vibrating like this, this would be the first critical. The first critical has two nodes and one antinode. The second critical mode shape looks something like this. In this case, there are three nodes and two antinodes. Here we have a structure resonating at its second critical mode shape. You'll notice that we have three nodal points and two antinodes. Remember, with resonance, if we're going to insert a brace, we need to brace it at one of the antinodes. If we brace it at the nodal point, it has little or no effect. If we brace it at either of the antinodes, we solve the problem. So it's not a matter of just making the structure stiffer. It's knowing where to put the brace. Again, if I was to go out into a real structure in the field, I could probably use my coin to actually feel the vibration across the structure, like this. And I could actually feel different amplitudes, intensities in that vibration. Now we'll do the third critical mode shape. This has 4 nodes and 3 antinodes. And this one is the third. Here we have the third critical mode shape. Notice there are 1, 2, 3, 4 different nodes and 1, 2, 3 antinodes. Remember, if we brace at a nodal point, it doesn't do any good. If we brace at any of the antinodes, the problem goes away. Of course, my speed varied just a little bit there. So that's resonant mode shapes. In many situations, that mode shape is apparent enough for you to detect it with nothing more complicated than a...
So basically we are going to make such plots. Okay. So we are actually looking at modes and mode shapes, and the structure is more complicated in the sense that these things depend on mass, they depend on stiffness, and the rate at which they decay is dependent on damping. Okay, so mass and stiffness, it means that if you change any one of these, you can very easily change the natural frequency of vibration and probably even the mode shape. Because structure has mass distributed throughout, it actually has infinite mode shapes, but there are certain mode shapes where the mass, where the system tends to show marked patterns of displacement, like what you saw there, the first critical mode. So that those are called the critical modes. And in all fairness, I'll add that why we need to do this is, if suppose we are going to take a real structure, we are trying to ensure that the mode of vibration is simple. So what is the learning we take from this dynamics course is that we don't like torsional modes. Okay, we saw the torsional mode on that scale. A building can also have torsional modes, but what we try to do is we try to arrange the mass and stiffness of this system in a manner that the first few critical modes are bending in nature. Okay, so it can take wrinkles in bending mode, so that's acceptable. But in first mode, preferably it has only one wrinkle, second mode has more wrinkles, first mode may be in X direction, second mode in Y direction, so on and so forth. And if the wrinkles increase, if you keep increasing the wrinkles, then quite frankly you will also see that the displacement reduces. And that has certain advantages which we will probably have a look at in the later part of our lecture. Okay, so the key learning is that in a structure we prefer bending modes. First critical mode should have as few wrinkles as possible, so that is the general rule of thumb. But if suppose you are having more wrinkles, that is bent shapes, it means that that system is not having as much displacement as you would like. I mean, you don't want much displacement basically, so it's safe for you. Coming to vibration, the other thing is periodic vibration. Maybe your heartbeat is periodic, the swing going up and down is periodic, air conditioner motor or the fan which is exciting the building is periodic, and random vibration is when periodic means the same force, same velocity, same acceleration is going to happen after a fixed interval of time. That's periodic. Now, random vibrations are when people are walking on the floor There's no need that the first footstep and the next footstep is going to be the same. Okay, and for this reason, if you remember, you would have studied, soldiers are asked to break step on the bridges. That means they don't allow them to march on bridges. What is the reason? They are exciting with a fixed frequency, left, right, left, right, left, right, left. Low frequency, if you remember, I mean, you will find that most of the buildings are affected by low frequencies. So that means these people are marching at low frequency. They are giving a repeated, what we call as excitation at fixed intervals of time. So that means there's a very good chance that their marching will coincide with the natural frequency of a bridge. So they will ask soldiers to break the steps. So then from a periodic it becomes a random excitation. Okay. Now there's another thing called phase difference. Okay. Now just have a look at this video. What is amazing in this? What is amazing in this? What is different in this video?
Fan is not running.
Yeah, the rotor is appearing not to be running. What they have done is, they have made the rotor, the camera's, what do you call as capture speed.
Facebook video. I saw in Facebook.
Okay, this I got from YouTube, to tell the truth. Again,
I didn't understand this.
right. So what happens is, the rate at which the camera has a refresh rate, like for example 50 hertz, so on and so forth. So they don't call it hertz, they call it frames per second, 50 frames per second. So they match the frequency of the shutter to the frequency of the blades of the airplane. So what happens is, the first blade, it turns one rotation. At that time it takes a picture, closes, opens, closes. So both of them are matching, so it looks like the blade is in the same position. Okay, so this is an optical illusion which you are getting from phase difference. Okay, so this is a word I want you to remember. So in phase, both of these things are in phase. That is, the blade comes here, at the same time the capture is there, off. So both of them are repeating the same action at the same time. So this is called phase difference. I will come back to this in a very short while today. Okay, so now you will be going to look. So today what we seen in this video basically is, or in the series of videos is, we saw that vibrations cause, like from the video of the swing, there is something which influences the time period, that is the mass and the vibrating length. Okay, and then we saw also that there are some very nice things which you can do with vibration. One of the things in a Newtonian fluid, you will find that viscosity is related to the shear rate. Okay, in other words, the velocity. And this is another term I am going to talk to you about in the next lecture. And other thing which we saw is where we were talking about the mode shapes, and we related it to the frequencies. Remember, there's one exercise I want you to go and do. When is the mode shapes mode? When the frequencies or so there are two things which are happening there. So you need to just have a look at what is influencing the mode shapes. Okay. So this is another thing which we also, and also the video clearly showed what a mode shape is. Okay, it clearly showed what a mode shape is. And going beyond, we also saw the other video where they showed it very clearly that mass and stiffness alone need not be changed to reduce the what we call as the response. The response can be also reduced by bracing a vibrating system in the correct position. Okay, because the easiest thing to do is to change the mass. In fact, we had a problem when I was working in L&T. One of the crushers which we installed, the foundation started to vibrate. Okay, similar crusher had been installed in other location, there was no problem, but here the foundation was a little different, or the base on which it was sitting. So the base started to vibrate because of the system which was working on top of that, and client was not happy. So what we did was we increased the stiffness of the system by adding a few walls, and by doing that, the natural frequency was of the foundation was away from the operating frequency or the excitation frequency. So this solved our problem. Okay. So we are going to talk a lot about this mass and stiffness, and you will also see that it is a very many places vibration problems will be there. So if you are able to understand the system, and if you are able to brace it, or change the mass, or change the stiffness, or change all these parameters in a manner that vibration is not observed, you are going to become a very sought after consultant. Okay. So please let's have a look at all the other parameters also here. So these are some of the references of the references which are used. And do you have any questions, please? Are you sure? Right, thank you so much. So in the next lecture, we will be having a look at some of the we'll have an introduction to some of the terms or equations in dynamics. Okay.